A lot of what I'll share here can be found in a book called Abrupt Climate Change: Inevitable Surprises, published by NAS, the National Academy of Sciences, which, as a professional organization, is at the very top of our credibility spectrum. You can actually read the whole book online if you Google around a little. In discussions about this with the skeptics, I often feel frustrated with their insistence on immediate and certain consequences before they would acknowledge the need to do anything. Sometimes I find myself thinking, what do I have to do? Say that global climate change is going to come to your house personally and eat your lunch? So here's where we see why it's not so outlandish that yes, global climate change may indeed come to your house and eat your lunch. The reason why this message may seem so different from what you've been used to hearing about climate change is that in just the last few years, an entirely new topic in climate change has emerged. That is the idea of abrupt climate change. We used to think that the climate of the past changed gradually, and 20 years ago, when climate models first started suggesting that we could change the climate, all the discussion was about it happening in hundreds or thousands of years. But as the science improved, the data collection, computer modeling, and understanding of complex systems, the predicted timescale for the change just got shorter and shorter. And this is where most of the scary stuff comes from. Unfortunately, it's not simply conjecture. Just in the last 5 to 10 years, we've come to see that the typical behavior for the climate seems to not be to change gradually, as we'd previously thought, but to actually hang in one state for a while and then suddenly lurch to a new state in a very short period of time, usually prompted by some sort of poke, some change in the conditions. And now the best, most recent science is suggesting that we may face the threat of climate changing very abruptly. That means within decades, perhaps even a single decade. This trend in the science itself of climate change, this trend of ever-increasing severity of predictions, is in itself frightening. Because in general, what science tells you today is more reliable than what it told you yesterday. In science, changing your mind is a good thing because it means your understanding is getting better, closer to the physical truth. So it's bad news for us that as time has gone on and the scientific picture about climate change has gotten clearer, it's also gotten more grim. One more reason to be nervous. So we no longer see the climate as something gradually shifting over millennia, but as something lurching from one extreme to the other, usually prompted by some sort of outside factor. Wally Broecker, the Columbia University climate researcher, whose work is the foundation of carbon cycle science, summed it up vividly, saying, "We are getting a picture of the climate as an angry beast, and we are poking it with a stick." This is one of the most authoritative climate dudes on the planet. Yikes! In order to understand how something as huge as the global climate can change in a geological eye blink, we need to first understand the nature of complex systems, sometimes known as nonlinear dynamical systems, or in the popular parlance, chaotic systems. I pointed out elsewhere that global warming is not a great name for the phenomenon, not only because some places get colder, but because the change in temperature may not be the main thing we'll notice. It's how the rapid change in temperature destabilizes the climate, affecting precipitation, droughts and floods, wind events such as storms, hurricanes, and tornadoes, and ecosystems, like with forest fires, agriculture, and permafrost. That will really matter to us. So how can such a small change so destabilize a global climate? Because the climate is a complex or chaotic system, so it's worthwhile to look briefly at some of the features that define a complex system. One of the main features is that the behavior of the system is extremely difficult to predict, hence the term chaos. General trends are easier to tease out than specific behaviors, sort of like it's easier to say that about 50% of coin tosses will be heads, but you can't really predict the outcome of a single toss. It's also why we can talk about the probabilities of what the climate may do in 20 years, but we have trouble predicting whether it's going to rain Tuesday or not. Another distinguishing characteristic is what's called extreme sensitivity to initial conditions. What that means is that tiny little differences can cascade into vastly different outcomes. Popularly known as the butterfly effect, it's not just fanciful, it's actually easy to observe. For instance, imagine two dried leaves floating on the surface of a swift river, right next to each other, almost on top of each other. One of them ends up hung up on a rock 10 yards downstream, while the other one finds its way to the ocean, even though they were placed almost exactly in the same spot. One objection you'll often hear when talking about climate change is how arrogant to think we can affect the planet. It's only common sense that we're too small to have an effect. Too small to have an effect? Tell that to a virus, or a mosquito in your bedroom when you're trying to go to sleep. In a complex system like the climate, very small differences can have huge effects. If you watch the video, The Nature of Science, you'll know that common sense is easily fooled, and is no way to make a decision about a complex topic. Here's a slightly geeky example, but if you stick with me, it can be a pretty cool realization. Here's a graph made by a fairly simple calculation, but the calculation is run again and again. It's designed to do a very basic population simulation of rabbits or wombats or javelinas or whatever, and it turns out to behave like a complex system. Note that the population over here is not in whole numbers like you'd expect. You can take the vertical axis to be in millions if it makes you more comfortable, but the dynamics work out the same. Across the bottom we have generations, and each one represents one turn of the crank of our simple calculation, one generation. You can see that the population goes up and down in a way that looks random or chaotic. You couldn't be expected to look at this and predict what the population of the next generation would be. Maybe you could describe some patterns, like it goes up and then it goes down, but anything more specific soon fails. Now here's where the really wild part of chaotic systems show up, because this graph is the exact same procedure as this graph. It's just that the initial population differs from this one by just 0.000002%. As you now take a look, and as you compare the population fluctuations between the two cases, you see that they track along nicely, identical as far as we can tell, which is what you'd expect because their initial populations were almost identical. But then when we get to population 50, suddenly, bam! The populations diverge wildly, and we suddenly have two totally different outcomes. Two completely different outcomes from initial conditions that were only as different as 5 million is from 5,000,001. That's crazy. That's wild. That's chaotic. And forgive the little circles there. This is my notes. These are my class notes. I didn't want to wipe that out and have you think I was doctoring the graphs. And if you recognize this as 10-year-old Mathematica code, you're what's known in the business as a terminal nerd. So next time you hear someone say, oh, but we're too small to make any difference in something as big as the global climate, you can just whip out your graphing calculator and show them this. Or maybe not. The reason that complex systems behave with such extreme sensitivity is due to another hallmark of a complex system: feedback. This is where you have some process with an input and an output, say like a microphone hooked up to a speaker. Here the input is the sound that goes into the microphone. The system, in this case the speaker, changes it, in this case amplifying it, and the speaker gives the output, in this case loud sound. In the population simulation we just talked about, the input is the number of live rabbits going into a breeding system, and the output is the number of live rabbits surviving at the end, and the system is all the things affecting bunny survival. Feedback is when the output of the system is then used as the input for the next go-around. It is fed back into the system. As you've probably experienced, the results can be painful sometimes. The reason feedback leads to the extreme sensitivity we mentioned a minute ago is because the process, breeding rabbits or an amp or whatever, in one turn of the crank, one go-round, takes small differences and makes them slightly larger. These results are then fed back into the system for another go-round, which makes the differences larger still, which are then made larger, and you can see how you can quickly get a result which seems way out of proportion to the original input. But that's not feasible, you say. That implies it would go on forever and run away. Well, eventually other factors do kick in and stop the change, just like the speaker doesn't continue to get loud forever. It bumps up against some limits. So the sound does level off, although that doesn't mean it's comfortable for us. How's it going? Nice weather, huh? This is why, with global climate change, it's not the temperature that scientists are worried about. Who wouldn't like to be just a little warmer on a chilly day? The problem is that even a small change in temperature can get amplified by feedback mechanisms, so that we would end up with a huge change further down the line, and not necessarily in temperature, but in some other characteristics of the climate, maybe in rainfall patterns, or storm frequency, or growing seasons. The changes from the conditions which trigger such abrupt shifts in the climate are called forcings. In the case of our speaker, the forcing would be the small amount of ambient noise which gets the whole feedback cycle started. In the past, the likely forcings which caused abrupt climate change were things like changes in the output of the sun, or the periodic wobble in the Earth's axis, or a large random event, say the breakup of a single ice dam releasing a huge lake all at once. The conditions at which a small tweak in the conditions causes a huge change is called a threshold, or in the popular press, a tipping point. In the video How It All Ends, I offered the analogy of flipping a light switch. Small pushes result in small movements until a tipping point is reached, when the same small movements that had done nothing much of anything before suddenly result in a big change, like flipping a switch, or like leaning a canoe over gradually until it suddenly tips. Or here, moving the mic 1/4 of an inch at a time does nothing. A little movement, little to no change. The same little movement, still little to no change. But at some unexpected time, the same little movement which had gone unnoticeable before